All right, let's talk about salts. And when we're talking about salts, we're talking about ionic compounds. So we're not talking about simple Bronsted acids or bases. We are talking about compounds of their conjugates. So we're looking here at pHs of the conjugates. What might we mean by that? We might mean something as simple as NaCl, or we might mean something like NH4NO3. And what we are going to look at as we do these consistently is we're going to try to find the conjugates in here to see if we can figure out what our pHs are going to be. So we're going to need a policy here. And the first policy is that the stronger the acid, the weaker the conjugate base. So stronger the acid, weaker the conjugate base. So if we have something incredibly strong like HCl, which we know if we put in water is going to dissociate 100% into H plus Cl minus, because this is strong and the reaction goes 100% towards products, the reverse reaction goes 0%, and this is in fact so weak as to be inert. If instead I looked at something like, let's say acetic acid, CH3COOH. Now this is a weak acid, and it's got an arrow going in two directions. Now the acid is stronger than the conjugate base, and that's due to a number of properties, and we will look at those in a moment. But here, because this is a weak acid, this reaction goes in both directions, and so this is going to be a weak acid, and its conjugate base is also going to be weak. Now one of them is going to be stronger. In this case, the acid is going to be stronger than the conjugate base. If we take a weak acid, HA, and we take its conjugate base, A minus, we can write the hydrolysis for each. HA is going to react with water to make two arrows in an ice, A minus plus hydronium. Now, A minus is going to react with water to make HA and hydroxide. And we know this because we can write hydrolysis reactions. And we can write our equation, our form of our Ks. If we take our Ka and we multiply it by Kb, we're going to take a look here, and our Ka is going to be A minus times hydronium over HA. Our Kb here is going to be HA times hydroxide over A minus. And if we start crossing out like terms, we're going to cross out our A minus and our HA, and we are going to get that Ka times Kb is equal to hydronium times hydroxide, which tells us that Ka times Kb is equal to Kw. Now we're always going to work at room temperature, which tells us that Ka times Kb will be equal to 1 times 10 to the minus 14. Now, why is this useful? One, because we can look up our Kas and Kbs. And we know that as one of these is going to get bigger, the other one of these is going to get smaller. And so the stronger the acid, the weaker the conjugate base. Acid. Now, very, very, very important on this. We knew we had to remember our strong acids and our strong bases. And we know our strong acids are HCl, HBr, HI, nitric, chloric, and perchloric. So, why did we memorize these? Well, we memorize these not because we need to have the strong acids memorized. And I know that sulfuric is on here, but sulfuric is a polyprotic, and we're going to ignore it for this purposes here. We're only going to look at the monoprotic ones. If this reaction goes 100% towards products, it is going to go 0% back towards our reactants, which tells us that because our acids are very, very strong, our conjugates are inert. What does this mean? This means if we have the conjugate base of any of the strong acids and we put these guys in water, they are going to give us a pH of 7. These are not acids and not bases. These guys are inert. And this is going to hold for the conjugate ions of the strong bases as well. So we know that sodium hydroxide and potassium hydroxide, lithium hydroxide, calcium hydroxide, and strontium and barium are our nice, strong bases. And this is going to tell us as well that if we have sodium or potassium or lithium or calcium, strontium or barium, and we put these guys in water, they're going to have a pH of 7 as well. And our conjugates of our strongs are going to be inert. So as we look for our salts and our acid-base properties of our salts, we are going to consistently look for the conjugates of the strongs. Why? Because they are going to be inert in the solution, giving us a pH of 7. All right, so we have salts. Now we know that salts are water-soluble ionic compounds, meaning that when we put these guys into water, they are going to break into its ions, and that is going to be our step 1, break into ions. So when we break these into ions, we're going to look at these and realize that we've made this up of Na plus and Cl minus. Calcium will be calcium 2 plus and 2 nitrates. Remember to leave your polyatomics intact. Don't mess with them. Just break off whatever of the other small piece you might have. And almost exclusively, we are going to have one of these as either the counter ion or the conjugate acid of a strong base, or we're going to have an anion that is the conjugate base of a strong acid. Why do we care? Because anytime we have any one of these guys, they are going to be inert. The conjugates of the strongs are inert, and our solution will be neutral, pH of 7. So if we go down here, we're going to look at these guys, and we're going to try to see if we can find conjugates of inerts. And if we do this, we're going to have Na plus, and here we've got calcium 2 plus. Here we have potassium. Now, if we look at our anions here are going to be F minus, C2H3O2 minus. Remember to leave your polyatomic anions and even cations here intact, and we have NO2 minus. So we've got to ask ourselves, are these acids or bases? Well, we know they're negative, and so if they're negative, they're going to be bases. They're going to be the conjugate bases of weak acids. If they're the conjugate bases of weak acids, the solutions are going to be basic, and we're going to have to figure out how to calculate their pHs. Now, ammonium chloride. If we're going to look at this, we're going to go, okay, we have ammonium, and we have something we recognize. We recognize chloride. We know that chloride is the conjugate base of HCl, and if we take that off, we're going to leave NH4 plus behind. This is inert. This is positive, and we know if we've got something that's positive, it's much more likely to be an acid. And if we look at this, this is the conjugate acid of NH3. And this is going to be an acidic solution, and we're going to have to figure out how to calculate its pH. So if we have a cation of a strong base, so for example, Na plus here, our anion, if it's the conjugate base of a weak acid, our solutions are going to be basic. How do we know? Because we've got conjugate bases. If instead our cations are the conjugate acids of weak bases, the anion is the conjugate of a strong acid, our solutions are going to be acidic. So I know there's a lot of words, but here's what you're going to do. You're going to take a look at it and see, is it a plain acid, is it a plain base, or is it a salt? If it is a salt, you're going to break it apart. And when you break it apart, you're going to see if you can find conjugates. So we're going to look for pieces we recognize. And the first thing we're going to recognize is sodium. We know sodium is Na+, and so the rest of this has to be some other acid or base species. And in this case, we're going to leave it intact. It is HCO3 minus. Because this has a negative charge, this is going to be the conjugate base of something. To figure out what is the conjugate base of, remember that conjugate bases are just related by an H+. So if this is a base, its conjugate acid is H2CO3. So what are we going to do? We're going to calculate the K that we need from the K that we are given. And again, if we have ammonium chloride, we're going to look for conjugates of stuff we recognize, pieces of stuff from the strongs. And in this case, the piece that we recognize is Cl. So this is Cl minus. This is the conjugate base of HCl. We know that this is inert, so we're going to ignore it. If we take off, we're going to have an NH4 plus left, and this is the conjugate acid of NH3. Cl minus. So let's predict if these guys are going to be acidic, basic, or neutral. So we're going to start from the bottom and go up. First thing we're going to do is we're going to break them into pieces. K plus and O3 minus. And then we're going to consistently look for inerts. Okay? If they are inert, we're simply going to cross them off because they're not going to affect our pH. So we're going to look at KNO3. We're going to realize that K plus is inert, NO3 minus inert, so our pH is 7, and this guy's neutral. Okay? NH4I. NH4I is a combination of NH4 plus I minus. I minus we know is inert. This is NH4 plus. This is going to be positive. This is the cation. Therefore, this is going to be an acid. Remember, our positive things are going to be acidic, and therefore our solution will be acidic. If we go into NaNO2, so if I go down here into NaNO2, I break it apart. I break it into Na plus and NO2 minus. Na plus, we know, is inert. We look at the NO2 minus. This is an anion. This is negative. Therefore, this is going to be a base, and our solution will be basic. Na2CO3. Well, Na2CO3 is made up of 2 Na pluses. Again, this little 2 here tells us how many of those we've got. And CO3, 2 minus. Sodium, we know, is inert. Carbonate is negative. It is our anion, which means it's going to be a base, and our solution will be basic, leaving us with the last one. The last one is aluminum chloride, and we go, okay, I have no idea what to do with this, all right, but we're smart. We know that this is made up of 3 chlorides and an aluminum. So for right now, we're going to guess, and we're going to guess here that this chloride is inert. In fact, we know that is inert, and we're going to say, okay, this is positive. Positive things tend to be acidic, and we're going to discover as we go through this problem here that aluminum 3 plus is in fact an acid. We're going to discuss that it is a Lewis acid. All right, let's look at these solutions and rank from the most acidic to the most basic. So if we're going to look at these, we know we're going to have our acids down here and our bases up here, and the species that are going to be neutral are going to be in the middle. So if we take a look at these and we look at NaOH, we know that this is a strong base, so I'm going to shorthand as a strong B. SB. HF is a weak acid. KCN is a mixture of K plus and Cn minus. And NaI is a mixture of Na plus and I minus. So the question then is now, what is acidic, basic, and what is neutral? So we know that NaOH is a strong base. So it is going to be the most basic. We know that HF here is the only acid, so it is going to be down here. If we look at the other two, NaI is going to be neutral. We know that because both of these are inert. And KCN is K plus, which is neutral, and Cn minus, which is a weak base. So our next species here is going to be KCN, with NaI in the middle being neutral. All right, let's look at this one. HNO3, KOH, NAF, Ki, and NaClO. Now, most of these are straightforward. Our HNO3 is going to be a strong acid, so we're going to put it right down here as the most acidic. KOH is a strong base, so it's going to be up here as the most basic. Ki here is going to be neutral, so I'm going to put it right here, and this guy is neutral. Now I gave myself some space to the right because both of these guys are basic. How do I know? Because we have NaF and F minus. We look at it and we know it is ionic. We're going to remove the inert species, which is sodium, leaving us with fluoride. This one is Na plus and ClO minus. Sodium is still inert. So the question is, which is a better base? So Ka for HF. And remember, with these guys, we know that Ka times Kb is equal to Kw. So if we compare the Kas for these two conjugate acids, in this case HF and HClO, we should be able to figure out which is going to be the strongest base. Well, Ka for HF is on the order of about 10 to the minus 5. Ka for HClO is on the order of about 10 to the minus 9. Now we know that the stronger the acid, the weaker the conjugate base. So if we look at these, HF is a stronger acid, therefore F minus is going to be a weaker base. HClO is a weaker acid, therefore ClO minus is going to be a stronger base. So this is going to have a larger Kb. So the Kb for ClO minus is going to be greater than the Kb for F minus. And so NaClO is going to be here, and NaF is going to be here, with the most basic going down to the least basic, or most acidic to the most basic. Which leaves us with the math. So we want to know, what is the pH of a 0.42 molar ammonium nitrate solution? So the first thing we have to do is figure out what this is. Now, this is the toughest of the salts because we don't actually have a metal. What we have is ammonium, and we know ammonium is a cation with a plus. And the other thing we know is that we have this NO3. Well, we know NO3 is NO3 minus, and this is nitrate. Because this is the conjugate base of HNO3, which is a strong acid, this is inert, leaving us with NH4+. Now, NH4+, if we look at this, we know that this is the conjugate acid of NH3. How do we know? Because if we look at this, we know that this, first of all, is the cation. Our cations are going to be our positively charged species, and if it's positively charged, it is much more likely to be acidic than anything negatively charged. So we have NH4+. We know that any time that we have an ionic compound, we're going to break it apart, and then we're going to calculate the K that we need. So we're going to look at these and realize if we have an ionic compound, it's always going to be made up of conjugates. So if we look at our conjugates, we know what we have is nitrate, which is an inert, and we have NH4+. We have NH4+. We know that this is the conjugate acid, conjugate acid of NH3. NH3 we know is a base. We can look up the Kb for this, and we know that when we're looking at conjugates, we know that our Ka times our Kb is equal to Kw. We look up the K for the one that is not the conjugate. K for ammonia, Kb, is equal to 1.76 times 10 to the minus 5. Just look it up in the back of your book. So Ka for ammonium is going to equal 1 times 10 to the minus 14 divided by 1.76 times 10 to the minus 5. And therefore our Ka for this acid is going to equal 5.68 times 10 to the minus 10. So what do we have? We have a weak acid. We have a K value, which means that we're going to need an ice chart, and we're going to need an X, and we're going to solve for something. So with that in mind, we know that NH4+ is an acid. All of our reactions are still hydrolysis reactions. So this is going to react with water. It is going to make ammonia. Because this is an acid, we know this is going to make hydronium. We know that our Ka, which we calculated from our Kb of ammonia, is 5.68 times 10 to the minus 10. And this is going to equal the concentration of ammonia times hydronium over NH4+. This is weak, so we need ourselves an ice chart. We're going to start out with the original concentration of the ammonium nitrate. It breaks up 100%, so this has a value of 0.42. We're going to ignore this because it's a pure liquid and these guys start out at 0. If this is the case, then we're going to take them. This is going to go down by x. Ignore the other dot there. 0.42 minus x plus x plus x, x, and x. And we're going to have 5.68 times 10 to the minus 10 is equal to x squared over 0.42 minus x. Our k is small, therefore we'll set that x equal to 0. We'll multiply through by the initial and take the square root, and we'll get x, which is equal to the concentration of hydronium, is equal to a value of 1.5 times 10 to the minus 5 units of molar. Our pH is a minus base 10 log of that. Giving us a pH of this solution equal to 4.81. We have an acidic salt. All right, let's try the pH of a basic solution. Now we have sodium formate. Now the fact that we really don't know what this is isn't that relevant because we know it's an ionic compound. How do we know? Because we have a metal and we have ourselves a nice polyatomic ion. We know we're going to take this and our nice salt compound and we're going to break it into pieces, and we're going to have Na plus and HCOO minus. We're going to consider that sodium is the conjugate ion of sodium hydroxide, therefore it's inert, leaving us with HCOO minus. Now HCOO minus is negative, which means it's going to be the conjugate base of something. Well, it's the conjugate base of whatever we stick that proton on, so that's going to be HCOOH is going to be the acid for which the formate is the conjugate base. So you're going to go to the Google in this case and you're going to look up Ka for HCOOH, and when you do that you find that the Ka for this acid is equal to 1.8 times 10 to the minus 4. So we know this is a conjugate. We know that this Kb multiplied by that Ka is equal to Kw, so that Kb for our formate is 10 to the minus 14 over 1.8 times 10 to the minus 4, and that is equal to 5.61 times 10 to the minus 11. So what's our reaction? Well, the sodium is inert, so we're going to have HCOO minus. Make sure you keep track of the charges when you do this. Otherwise, you might get here and forget that this thing is a base. So if we have HCO minus, it's going to make the conjugate acid. Because this is a base, it's going to make ourselves some hydroxide. We've got 2 arrows, so we need an ice chart. We're going to start out with 0.24. We're going to ignore the water because it's a pure liquid. Have 0 and 0. This is going to go down by x. Plus x plus x. So that down here we have x and we have x. We have Kb, which is 5.61 times 10 to the minus 11, is equal to x squared over 0.24 minus x. We know that our k is small, therefore we can set this bottom x equal to 0. We're going to get that x, and the key on our pH questions is that x here is equal to the hydroxide. And when we finish this, we're going to get that x is equal to 3.7 times 10 to the minus 6 molar. We're going to get POH first. POH is a minus base 10 log of that value, which is equal to 5.43. We remember that pH plus POH is 14. Therefore, pH of this solution is 8.57. It is weakly basic. All right, let's do one more. Aniline hydrochloride, which really they do call these things because we look at this, and first of all, if we look at our compound, this is some sort of cation attached to chloride. Now, industrial or medically, we don't call it chloride, we call it hydrochloride, but nonetheless, it really is a chloride. So it's Cl minus with C6H5NH3 plus. Now, if we keep track of the charges, we can do this problem. We know that this is inert. We know that this is a conjugate acid of some base. So what base is it the conjugate acid of? Well, if we have C6H5NH3 plus, We know that the base that it is the conjugate acid of is C6H5NH2. This is called aniline. If we Google this, we can get a Kb for this base. Obviously on a test we would give that to you, but we can give you the Kb for this, and that works out to 4.3 times 10 to the minus 10. We know that Ka for this acid multiplied by Kb for aniline is going to be Kw. So the Ka for the C6H5NH3 plus is equal to 10 to the minus 14 divided by 4.3 times 10 to the minus 10. Give myself some space here. And our Ka is going to work out to be 2.33 times 10 to the minus 4. Now, since we have the Ka and we have the initial concentration, we know that this is an acid, we can solve for the pH. So our reaction is C6H5NH3 plus H2O is going to go into the conjugate base plus H3O plus. Our initial concentration of this acid is 0.233 molar. We're going to know the water, and these are zeros. This is going to go down by X, up by X, up by X, X and X, giving us a Ka, which we calculated on the previous page, of 2.33 times 10 to the minus 4 is equal to X squared over 0.233 minus X. We're going to set this bottom X equal to 0 because we're hoping that K is small. This is getting big enough that it might not be. When we turn around and we solve for this, we get X, which is equal to the concentration of hydronium. And when you do these problems, always keep track of what you're solving for, hydroxide or hydronium. When you solve for this, X is 0.0074, and the pH of this solution is equal to 2.13. If you calculate the percent ionization, you will discover it's less than 5, and this is a perfectly good assumption.